Welcome. We seem to have excellent attendance today, which is great. We're going to be doing a tutorial on the facilities in the Walla libraries for analyzing JavaScript. And just to give you an idea of the structure, I should introduce myself, I guess, first. I'm Manu Sridharan, and this is Julian Dalby and Max Schaefer. And the plan is for each of us to talk for roughly 50 minutes. And then we're going to have 15-minute breaks. So I'll go for the first 50 minutes, then we'll have a break, and then Julian will go another break, and then Max will finish it up. I'm happy to answer questions if anything is unclear as I go. Yeah, I guess that's about it in terms of upfront stuff. The slides are available if you want to download the PDF and be able to flip through them as we're talking. tinyurl.com/wallajs1, or I don't know. We could show you the URL again later. But yeah, with that, let's get started. So, what is Walla? It's a set of libraries implemented in Java mostly for doing static and dynamic program analysis. And very recently, we've actually open sourced some libraries implemented in JavaScript, which we're going to talk about later. But this has been developed over many years at the IBM T.J. Watson Research Center, was released in open source in 2006 under the EPL. And if I had to nail down the design goals for the Walla system, they would be robustness. So we're shipping this framework in products, so we care about handling corner cases and not just crashing. Efficiency, things are architected so that if you care about performance, hopefully Walla won't get in your way. And also extensibility. If you want to be able to customize the built-in analyses, there are many facilities for doing that in various ways. So in terms of what Walla has been used for previously, based on a Google Scholar search, rough count is over 100 publications. It's a little bit rough, including there are going to be 2 papers here at PLDI 2013 that make use of Walla, at least 2, I should say. And you can go to that webpage if you want to link to some of the publications. In terms of usage in products, there have been a bunch of examples. There was a tool called Rational Software Analyzer for finding bugs, and Walla was used there. It's used, this says Rational App Scan. I believe it's now IBM Security App Scan for a number of things, and including the JavaScript call graph support is now part of the product. And actually, interestingly, the whole JavaScript front end was initially motivated by this product, Tivoli Storage Manager, back in 2005, which was doing some configuration in JavaScript. And so Julian built the JavaScript front end, the first version of it, in order to build some tooling for that tool. So it's been around and it's been used for quite a while. So what kind of features are built into Walla that might make you want to use this framework for whatever kind of program analysis you'd like to build? So we have some very mature pointer analysis and call graph construction algorithms. There are several provided. For JavaScript, you'd mostly be interested in variants of Anderson's analysis, but there's also rapid type analysis if you're analyzing a language with types. But we don't have that in JavaScript. These are all highly customizable. We're going to talk later on about how you can customize the context sensitivity policy and tweak it in various ways. And they're also tuned for performance, both in terms of running time and space consumption. There's also an interprocedural data flow analysis framework. It's the tabulation solver as described in this sort of classic Reps, Horwitz, Segev paper, but with extensions to handle things like methods returning exceptions, this kind of thing. And this has also been tuned for performance over many years.
So you mentioned even if you're analyzing a language with types, so this isn't exclusively for JavaScript?
No, in fact, one of the things we're going to try to explain is how we've taken this Walla framework, which is originally designed to analyze Java bytecodes, and how we've had to adapt a JavaScript analysis framework to make good reuse of all that functionality. But in truth, yeah, Walla was originally designed to analyze Java bytecodes specifically, and some of those warts will show through in the JavaScript front end.
Well, that's good, because what I'm actually interested in is Java bytecodes.
Oh, okay. Well, most of this will be focused on JavaScript, but you'll learn some stuff about the Java bytecode stuff too. Okay, other questions? Okay, so in terms of other key features, there are multiple language front ends. We're going to focus on JavaScript here, but in case people are interested, there's also a Java source code front end based on Eclipse JDT. I believe there's an X10 front end that's also open source for people familiar with that language. Is there anything else in open source that I'm forgetting? I think that's about it, but we're going to focus on JavaScript here. There's a lot of generic analysis utilities and data structures, so efficient graphs, sets, maps, constraint solvers. We're not going to get into a lot of detail on this functionality in this talk, although I'll mention that we did another tutorial on Walla at PLDI 2010. Those slides are available online, and they do give a bit more detail on this generic functionality. But all this code is actually completely independent of which language front end you're using. So in principle, you could just suck out these data structures from Walla and not use any of the Java or JavaScript support if you wanted to. One caveat that I want to mention up front is that there's very limited support for code transformation in Walla. Walla is designed more to compute properties of code, but not to transform it. So in particular, the main Walla IR is immutable, and there's no code generation backend for that IR. Now, for the JavaScript front end, we create ASTs that are translated to IR, and those ASTs can be transformed, and in fact, we do it in some cases, but that's a fairly advanced technique. And honestly, if you were just going after some code transformation, Walla would not be the way to go. And in general, I think our recommendation is you want to use Walla for computing your program analysis results, particularly if you're doing some kind of interprocedural analysis, but then perhaps do the transformation separately using maybe some framework that's targeted, say, to rewriting JavaScript code. And in fact, Max is going to talk about this later. As part of the JavaScript libraries that we've recently made available, there is a normalizer for JavaScript that translates it into a simpler form that can help simplify other dynamic analyses. So we are going to talk about that a little bit later on. So at a high level, what we're going to cover in this tutorial is I'm going to start out just with some basics of the call graph APIs. As I'll explain, call graphs are pretty central in Walla, so that's why we're kind of starting there. Then I'm going to talk about how scripts and methods are represented in terms of Walla data structures, and this is where maybe some of the warts are going to show in terms of trying to build this JavaScript front end on top of a framework that was originally designed for Java. I'm going to talk about all the functionality that we have for representing HTML and the DOM. And then Julian is going to talk in some detail about the IR that's used by Walla for representing JavaScript. And as I assume many of you know, JavaScript is a rather complicated language. And so there are some nasty things that we have to handle. And we've done our best in the IR to capture them. And Julian's going to talk about some of those details. Finally, Max is going to talk about some of the customization features we have for call graphs. And also going to discuss these libraries that we've recently open sourced that are implemented in JavaScript. And if time allows, maybe cover some more of these advanced topics. Okay, so any questions at this point? Okay, so one last thing, just a brief slide on how to get the Walla code. So there's a Getting Started page on the Walla homepage, which I've actually recently updated, so hopefully it's fairly up to date in terms of how to grab the code, get it to compile, and so on and so forth. All the code is available on GitHub, so you can go to that site now and just clone the whole repository if you like. we've developed Walla in Eclipse. So in many ways, it'll be easiest for you to work with Walla if you're working in Eclipse. That said, recently we've re-architected things so it's not as necessary as it used to be. But in terms of the structure of Walla, it's split into several Eclipse projects. So I've just listed a few of the most relevant here. So, and all of these I've left off the com.ibm prefix on this slide. So the Walla util project has all these language-independent utilities like graph, sets, maps, and so on. The Walla core package has the program analyses we've implemented for the sort of core Walla IR, and this includes a lot of Java bytecode relevant stuff. And then we have this CAST framework, which stands for Common AST, and that's some generic code that's shared across all the AST front ends. And then Walla CAST.js has the JavaScript specific stuff, in particular IR generation and analysis extensions to handle JavaScript semantics. And then Walla is actually architected to support multiple JavaScript parsers, and there's a separate Rhino package that has the front end for converting the Rhino parsers ASTs into our own. And I think I actually covered this bottom part. So one thing I'll mention is that recently we've added some Maven build support that's documented on the Getting Started page, but hopefully that will be helpful if you're not an Eclipse user. Okay, so let me jump right into the call graph basics that we're going to start off with here. And the reason that call graphs are so important is, in some sense, Walla was kind of designed with the idea of making it easier to do sophisticated interprocedural analyses. And usually, when you're doing an interprocedural analysis, the first thing that you need is a call graph, just to know what procedures are being invoked from where. So in our call graphs, you have nodes for the methods of your program, possibly cloned, depending on whether you have a context-sensitive call graph or not. And the edges represent possible call targets at all the call sites. Now, very often, I would say almost always, at least in Walla, when you're building a call graph, you do so by computing a pointer analysis. In other words, tracking the flow of the objects in your program and figuring out for each variable what objects it might point to. So almost all the call graph builders in Walla construct a call graph in this manner by computing a pointer analysis. So you'll see in the APIs that you sort of compute a pointer analysis by computing a call graph. In fact, this will be clear if I just flip to this slide. So there's a key type called call graph builder that you configure with your various properties in terms of context sensitivity and other sorts of things. You invoke make call graph on it, and that actually executes the call graph builder and returns to you a call graph. But after you've run this method, you can go back to the builder and call get pointer analysis, and that'll return a representation of the pointer analysis result that was constructed while building the call graph. So in a bit more detail on these APIs, so in our call graph, the nodes are of this type CG node. And you can think of this as a pair consisting of an I method, which is a representation of the method itself, and also a context, which can vary based on the context sensitivity policy. So essentially, if you have a context-sensitive analysis, you'll get cloned copies of a method where the I method will be the same, but the context differs. Walla is designed such that when you're trying to get an IR for some method, it's typically obtained from one of these CG nodes. You can't get it directly from an I method. And this is just part of the design of Walla. There are ways to get it if you have only I methods and you haven't built a call graph. In fact, I'll show that to you later. But the standard way of doing things is to get a call graph, and then you get IRs for different call graph nodes. So just to briefly cover some of the API, call graph implements the iterable interface, so you can loop over all the nodes in a call graph with one of these Java for loops. If you want to find all the callees of a node, you can call get suck nodes. It's part of the standard graph interface in Walla. And if you have a particular call site inside a node and you want to know what can be invoked at that call site, There's a method on call graph, get possible targets, that will tell you that. And you need one of these call site references, which you can obtain from the relevant IR instruction that performs the invocation. It's an abstract invoke instruction. Okay, so along with call graphs, we have the pointer analysis. So there's some more detail, I believe, in the previous tutorial slides and on the Walla wiki on these, but just briefly. The pointer analysis abstracts pointers using the pointer key interface, and it abstracts objects using this instance key interface. Okay? So you'll have different types of pointer keys for different types of pointers. So for a local variable, there's a type called local pointer key. For a field of an object, there's a type instance field key to represent that kind of pointer. And there's a type called a heap model, which you can obtain from the pointer analysis. That essentially, this is how you get pointer keys for a particular pointer analysis. I just showed one example here of how you'll get them for a local variable. So instance keys, again, are abstractions of an object. You can imagine in other languages some kind of type-based abstraction where you have one instance key per type. More commonly, say in JavaScript, you have an allocation site-based abstraction. So for some, say, object literal inside your JavaScript code, we'll have a particular allocation site in node object representing all the objects that can be allocated by that statement. And you can call get points to set on the pointer analysis with the pointer key, and you'll get back a set of instance keys that tells you what it can point to. So this stuff is hopefully not too complicated. So just to give you a very simple code example, if we want to build a call graph for some HTML file or page, you start out with the URL, which you obtain, however. Like I said, this can be a file, or I believe it can be a network address too, right? And then one thing we have to configure is we have to tell Walla that we're going to use Rhino to parse JavaScript. So that's just this line of code, which you pretty much stick at the beginning of any JavaScript analysis. And then we have a single API method, which, given this URL, will build the call graph for you. And then you can go from there in terms of the call graph. And Max will talk about how you can customize this in various ways if you need to. Any questions at this point? Okay. So now that I've gotten some sort of basic terminology out of the way, I'm going to dig a little bit more into how JavaScript code is represented in Walla. And let me start by describing a couple of the key data structures here. So there's an analysis scope, which represents, what code should be analyzed. And mostly this is pretty invisible when you're doing JavaScript analysis. When you're analyzing Java, this would contain, all the different jar files that you want to be available. And you'd probably have to deal with this data structure more. But it's not too visible for JavaScript analysis. One thing I'll note, though, is that we have models of the standard JavaScript libraries, which are themselves written in JavaScript. So in particular, there's this file prolog.js, which models the JavaScript standard library. And that will always be in your analysis scope, along with whatever scripts you want to analyze. So the other key type here is this I-class hierarchy, which does what you would expect in terms of representing a type hierarchy. And clearly this is coming from the Java world. This is very useful for Java where you have classes and subclassing. That aspect of it is less useful for JavaScript. But it also serves another important role, which is it's via the class hierarchy that you resolve names for different code entities like methods or fields to their actual representation. I'll get into this more on the next chart, but this is separated so that a name for a method in Walla is a method reference, whereas the data constructor that actually holds information about it, like its code representation, is the I method. And the reason this is useful is because once you compute your analysis, you can represent all your results using just the references, and this allows all the other stuff to be garbage collected. So it can potentially save a lot of memory if you're doing a Walla analysis as the first phase of a bunch of other things. The point here that's important is that when we were building the JavaScript front end, in order to reuse a lot of these core Walla analyses, we needed to have an I-class hierarchy, say to reuse the pointer analysis and call graph stuff in particular. So this is a slide that's mostly copied from the previous Walla tutorial that shows how different entities are resolved via the class hierarchy. So for classes, the reference is a type reference, and the resolve type is an I class, and you call this method lookup class on the class hierarchy to resolve it. So the question here is, what do these things even mean for JavaScript? We had to ascribe them some meaning. And this is actually, probably one of the more confusing aspects of this JavaScript front end. And so I wanted to just walk through this in a detail. And so one piece of good news is that fields basically mean nothing. In JavaScript, you don't have declared fields, so they're essentially strings. You'll see an I field floating around every once in a while, but all it is a string. You don't need to worry about resolving it via the class hierarchy or anything like that. So getting to the more interesting cases, what's a class in JavaScript? So the way we represent this in Walla, an I class, somewhat confusingly, represents a JavaScript function. And this includes a function for the top level code in a script, right? So when you're writing JavaScript, not all your code is nested in functions. You can write code at the top level. That itself is a function. And it also includes all the library functions from the prologue. Each function is kind of represented as its own I class. And then for well-formedness in terms of the Walla data structure invariance, all of these classes, at least in the data structure, subclass some kind of synthetic root type. There's a few other classes for built-in JavaScript types like Boolean and string, but this is something that you probably won't have to worry about. And I will tell you why you have to care about this. So that's coming. In fact, it's coming here. So if classes are functions, what the heck are these I methods doing then? Well, so JavaScript has very interesting semantics for how you can invoke functions. So there's a normal function invocation where it's what you would expect, right? You just call the function. And we represent this in Walla as a method essentially named do on the corresponding I class. So, I mean, it's a little bit, so why do we have a separate representation? Because you can also invoke methods as if they were constructors by adding the new keyword in front of it. And this has very different and potentially confusing semantics. So during call graph construction, when we observe these constructor invocations, we actually generate some synthetic code to model those semantics. And we store that code in another I method on the same class, which has a name ctor for constructor, which is different. So this is why you'd have two different I methods on an I class that is purportedly representing a function already. So one thing that's important is that if you're looking in Walla for a particular function that corresponds to some source level function, you have to look at the name of the declaring class of the I method, because the I method itself is just going to have some stub name like do or ctor, but the containing class will have the actual name from the source code. And so just as an example, we have this sort of trivial source.js file, which declares a function f, which also has a nested function g. We'll have three functions in Walla for this file. So there's source.js itself. This is the top level code that declares the outer f function. And then you have source.js/f for the f function, and then /f/g for the most nested function. JavaScript code typically has many anonymous functions that don't have names. And for that, you'll just get some auto-generated name for each sort of level in the nesting where you didn't have a source level name. Okay. Oh, yeah, question, sure.
So I understand that there is additional semantics that take place when a constructor function is called. But does that truly necessitate a separate representation, or could you have used a single representation for those and just added that additional machinery point where the constructor is actually being called, as opposed to incorporating inside the function.
So I think Julian's going to get into this in more detail. I think my feeling is that there are certain very nasty corner cases where trying to do everything at the call site and just having an invocation of the normal function would be inconvenient. Is that
the semantics at new really looks like essentially a dynamic dispatch, which is why we model it that way.
so? Julian's going to get into more details about what exactly we do there.
So it's mostly for library functions, really, for built-in native functions. So source level functions they always have the same meaning when you invoke them using new, but the library functions not necessarily.
Yeah. Okay. So just to walk through another chunk of code, which you don't need to understand in its entirety, but this is just to kind of keep me honest and not hide everything. So this is code that we're going to take in a file name, and we're going to try to print out the IRs of all the methods. And this is going to show you how to do it without constructing a call graph. So again, we're going to set up things so that we're using Rhino to parse the JavaScript code. And then we need to build one of these class hierarchies, which I just talked about. And there's a utility that'll build a class hierarchy for you for a bunch of JavaScript. Now, this somewhat ugly thing here is an IR factory. And the reason we need to construct this is because, again, we're not going to go through a call graph to build these IRs, so we sort of have to manually construct all these factories ourselves. But once that's around, we can iterate over the class hierarchy. Now here, we're getting the name of this class and converting it to a string. So remember, that's actually the source level function name, because classes are functions. And we're checking if it starts with prolog.js. So we're trying to ignore all the standard library functions. We don't want to print out their IRs here. So if it doesn't begin with prolog.js, we're going to get the method that corresponds to this do method, sort of a standard invocation. And this is just a constant that helps you do that. And if it's not null, we'll build an IR and print it out. So this print IRs class is actually part of Walla. So just a very simple example that you can go and look at if you like. Just to get a basic idea of how to get something going for a particular piece of code. And it can be instructive to print out IRs just to see what's going on for different models. Okay. Oh, question.
What kind of code is this intermediate representation? It's a stack-based, like bytecode, or as
no,
address code?
It's 3-address code and SSA. So Julian is going to spend a lot of time digging into how various things are represented there. But yeah, it's a 3-address code. Other questions? Sure.
Trying to represent this JavaScript class hierarchy in the static, which we originally used to represent the Java static type system, right?
Yes.
Is there a dynamic change in the semantic classes will affect or will bring any difficulty for you to do this? Is it convenient? Is there a problem in that case?
So you're asking about mutating the class hierarchy as the analysis goes?
In the scripting language that we can change the field name of the objects.
Oh, so you're talking about actually changing, say, the types of an object, say by overwriting its prototype or something like that. So none of that is modeled directly in the Walla class hierarchy. I mean, I don't think you can use the class hierarchy to approximate anything like the instance of functionality in JavaScript. It's basically just there so we can reuse all this machinery we have for call graphs and pointer analysis. And we just want to make that code happy by building this data structure that it needs. But I wouldn't think of the semantics of this class hierarchy as necessarily relating in any way to, say, prototype inheritance in the JavaScript code itself. It's kind of a kludge, but it lets us reuse a lot of code that's been sort of tuned for a long time. So that's why we did it. Okay, so moving on to the next topic, I wanted to talk a bit about the support for modeling HTML in Walla, which is actually fairly extensive and can be quite handy. So we have built-in support for actually extracting JavaScript code from an HTML page, and this includes script tags where the scripts are declared inline or declared via URL somewhere else. And also we have some support for even extracting JavaScript code declared in attributes on other HTML nodes, and I'll show that in an example. Could you pour me a cup of water? We also have support to actually generate a JavaScript model of the DOM structure of your static HTML. But this can be useful because, you know, one of the big parts of JavaScript is this DOM data structure that gets built up and that is accessed all over the place. And we do have a pretty decent model of some of its semantics. I mean, far from complete, but it covers a good amount of stuff. We also have built-in models of a lot of the DOM APIs in this preamble.js file. And this is necessarily incomplete. I mean, new APIs are appearing every week, but a lot of the core ones are covered. We also have modeling of some of the special semantics of JavaScript when it's run in a browser. For example, the window object and how it relates to the JavaScript global object is modeled in Walla. And finally, we're able to provide very detailed source locations for JavaScript code, including for when the case that you have JavaScript declared inline in HTML. We can give you enough information to sort of figure out where that code is. So let me just start out with an example here. So we have our HTML on the left here. We have one script tag declaring this function fizz that just alerts a message. And then we have an anchor tag that when you click on it, runs this fizz function. So you're going to see a little link, and when you click on it, it's going to pop up an alert window. So we generate a JavaScript model of basically all of this HTML. So create this synthetic window main function and what's in it. So we suck out the code from this script tag, just declare it here. That's this fizz function. We're also creating kind of synthetic DOM objects for all the other nodes that you see in this HTML. So we have a DOM object for this anchor node. We have a DOM object for this script node, and you'd see ones for the body node also. And it also captures their nesting, the sort of parent-child relationship. You can see here that we've extracted this function call into an assignment to this onClick property of this DOM node. So this onClick property gets a function that invokes fizz. And finally down here, we have some kind of imprecise model of user interactions with this page, right? So we generate this loop that is going to just say repeatedly click on this link. So particularly if you're building a call graph and you want to reason about what code is reachable, this model is going to make this code reachable, right? Because we're sort of saying we're going to assume the user is going to just click, 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 click on this link. And if there were other attributes, we would have executing that code as part of this while loop as well. So this kind of gives you an idea of the kind of modeling that we're doing of the HTML.
But if
Sure.
you have, for example, two on-click attributes, you generate all possible interleaving of the way you can click on them or not?
I don't think so. I think we have a flow insensitive model, so it'll look like a sequence of code rather than some kind of non-deterministic conditional. But I guess that
It's wrapped in a while loop, so it's
it is wrapped in a while loop, but it would kind of look like you were necessarily doing everything in each iteration.
that's right. Yes.
So it's not quite what you want. I mean, I should say that I don't think that would be too hard to modify it to do. That would be a great contribution.
Yeah, you could wrap it in a switch statement.
Yeah, that would just be just a bit of code generation to slightly change how it's modeled, but that would be very easy to add.
Okay.
Yeah. Right. So some high-level points on the HTML modeling, which is that so all the JavaScript code that appears or is referenced from a particular HTML file is nested inside this window main function. And part of the reason for that is to help model this fact that the variable window is kind of aliased with the global object when you're running JavaScript code in the browser. If you're not super familiar with JavaScript semantics, maybe that makes no sense to you. And we're not going to get into a lot of detail here, but it is important for capturing what's going on in this code, because essentially you can invoke methods on the window object by just calling them without writing window there. And we need to be able to figure that out. Hey, that might be a method of the window object, and then look up our appropriate model for it. So we have some handling of that. This generated JavaScript model, this code here, is by default stored in some temporary file that gets deleted when Walla exits. But there's this type JS source extractor where you can set a couple of flags to say, you know, retain that file after the analysis if you want to look at it, or, you know, don't use a temp file. Use some file in the working directory. We also have an option where you can extract the JavaScript code from the HTML, but you can avoid modeling the static HTML DOM. Sometimes this is useful because for a very big static HTML file, that can actually dramatically bloat the amount of code that you're analyzing. If you're just interested in the JavaScript, but maybe not interested in how it's interacting with the DOM, you can use this DOM-less source extractor so that you know, essentially the model will be much smaller. By default, we use this open source Jericho HTML parser. We also have support for this new validator HTML5 parser, which I guess is fully compliant with the latest parser specs, and that's all in open source. So you can switch the HTML parser if you like. And I wrote this example inside that print_irs class. Print_irs for HTML. So if you look up that code, that sort of shows you the same example that I showed you before, but iterating through all the code that you'd get for a particular HTML file. So that's a good maybe place to start if you're interested in knowing how IRs look for HTML-based JavaScript. Okay. Wow, it's going faster than I expected. So please ask questions. We're not crunched on time yet. So let me finally talk a bit about source positions, because this is, you know, quite important for reporting analysis results and showing them to people. So for JavaScript code, assuming that you're using Rhino as your JavaScript parser, usually we're able to provide the starting line and also the start and end offset in the file for each method and also for each instruction in our IR. So this is pretty detailed information. So for a particular method, if you want to get its source position, you downcast it to an AST method and invoke this get source position method. Similarly, there's a get source position method for IR instructions. So given its offset in the IR array, you can pass that offset here to get the location. One thing that's slightly more complicated is when you have scripts inside HTML. And in this case, we provide one of these included positions. So what goes on here is that the top level source position will give you like the start line and the offsets within the script itself, right? So if you have a script declared in HTML, it treats the first line of that script as line 1. And if you want to figure out where that script tag sits in the enclosing HTML file, you call this get include position, and that will tell you where the script tag is. So you can combine the two of them. Say you wanted to highlight some code in JavaScript that's declared inline in an HTML file. You could combine these two positions to actually find the exact location in the HTML file where it sits. So this is we have pretty good support for being able to nail down exactly where a particular piece of code is. So I think that's actually all I had for my portion of the tutorial. So I mean, are there any more questions at this point? Otherwise, we can just take our first 15-minute break now. Any other questions? Yeah.
So a couple of times you put assuming Rhino in the application and before that you can use other options. What changes when you are not using Rhino?
So in open source, basically the only thing that's supported is Rhino. Okay. We have this IBM JavaScript parser, which I think is still maintained, that gets used internally for certain applications. In principle, you could add support for another JavaScript parser, though I mean that's going to be a moderate to large amount of work potentially. Well, not large, but it's going to be a moderate amount of work. But all that changes, really, assuming that our APIs work properly, is that that very first line would change. And instead of providing the Rhino factory for parsing things, you'd provide something else.
Okay.
And then everything else should just work as is. Now, I mean, if your other parser does not provide the same kind of source locations that Rhino does, then some of these methods are just going to return -1 rather than the actual start offset or something like that. But none of the other APIs, how you invoke them, that doesn't really change at all.
One of the issues is that there's this language JavaScript that's defined by various ECMA specs. And at one point we were using, for some purposes, an internal IBM parser that was a very faithful implementation of this spec down to every last weird detail of the grammar. And what you quickly discover is that it's nice in a way to be able to parse JavaScript. On the other hand, it turns out that nobody on the web actually writes JavaScript. It turns out that Rhino, for instance, has relaxed certain rules that were put in very deliberately in ECMAScript are relaxed in Rhino, and everybody relies on this. And so for some internal historical things that we were doing with JavaScript at IBM, that other parser was useful, but on the web so far we really only use Rhino.
Other questions? Okay, so